wasn't even doing that. I was just out, with the construction. I was sort of representing. Saying the questions I answered when there was problems. Basically that, yeah. I was telling them. I still probably could have came down. You have to go to the beach? No.
Yeah, by 18. Oh, pretty good. I'm not sure about your winds.
I was up.
Well,
Stop.
okay.
Stop.
Which, by the way, hasn't stopped professors in time memorial.
Good afternoon, everyone. Thank you so much for being here. My name is Deb Franco. I'm the Senior Vice Provost for Academic Affairs. Provost Jim Bean sends his regrets. He had, unfortunately, a travel time today and so couldn't be here. He was sorry that he could not make it. I am honored to be able to introduce this year's Klein Lecturer, and I am delighted to welcome you to the 54th annual, that's a lot, Robert D. Klein Lecture. In 1964, the university established the University Lecturer Award to honor a member of the faculty who has contributed with distinction to his or her own field of study, and a lecture that allows the faculty member to share the fruits of that scholarship with the university community as well as the general public. In 1979, this award was renamed the Klein Lecturer Award in tribute to the late Robert D. Klein, professor of mathematics, chairman of the Faculty Senate Agenda Committee, and vice chair of the Faculty Senate. The Klein Lecturer is selected from a group of many esteemed nominees by a committee consisting of the chair of the Senate Agenda Committee, who this year is Dr. Susan Powers-Lee. She's with us there. This year, the past year's Klein Lecturer, who is Dr. Stacy Marcella, and myself. This year, as you know, Dr. Jerry Hajjar has been selected as our Robert D. Klein Lecturer. I'm going to do his bio now, so hang on, because he's really something. Dr. Hajjar is the CDM Smith Professor and Chair in the Department of Civil and Environmental Engineering at Northeastern University. He joined us in 2010. Prior to that, Dr. Hajjar served as Professor and Narbi Kachurian Faculty Scholar, as well as Chair of the Structures Faculty and Deputy Director of the Mid-Atlantic Earthquake Center at the University of Illinois at Urbana-Champaign from 2005 to 2010. He received his PhD in structural engineering from Cornell University in 1988. Dr. Hajjar is the director of the Laboratory for Structural Testing of Resilient and Sustainable Systems, the STRESS Laboratory, which is located at our Burlington campus. His research and teaching interests include analysis, experimental testing, design of steel and composite steel concrete structures, regional modeling and assessment of infrastructure systems, and earthquake engineering. He's published over 200 papers and authored or edited 4 books on these topics. Dr. Hajjar serves on the American Institute of Steel Construction Committee on Specifications, and this committee writes the national design specifications for steel and composite buildings. He's the past chair of the Executive Committee of the Technical Activities Division of the American Society of Civil Engineers Structural Engineering Institute. He was made Fellow of the ASCE in 2007 and of the Structural Engineering Institute in 2013, and was awarded many, many awards. In 2016, the ASCE Moisef Award, the 2010 Popular Mechanics Breakthrough Award. There are a lot of them, hang on. 2009 Shortridge Hardesty Award, 2005 Higgins Lectureship Award, and on they go. In 2000, he won the Norman Medal for his research on steel structures, structural stability, and earthquake engineering. And if that weren't enough, he has also won several teaching awards, so he really does it all. His talk today is called Urban Engineering, New Designs for a Resilient and Sustainable Future. His lecture will be followed by a question and answer period, the presentation of the Klein Lecturer Medallion, and then we'll have a reception in this room following. Please join me in welcoming Dr. Hajjar.
Thanks. Well, good afternoon, everybody, and thank you so much for the introduction. I didn't realize you were going to go through all of that. I'd like to thank you all for being here today, and I'd especially like to thank Deb Franco, Provost's Office, the Selection Committee for this recognition. I am truly appreciative. I'd like to thank all of my colleagues, both faculty and staff here at Northeastern University. It's really only through these great collaborations that we've been able to do the work that I'll be showing you here today. And I'm especially happy to see a lot of the students here today, including all my students who are sort of scattered throughout the room. They are dedicated, they work very hard, and I love working with them. And I hope you see that reflected in what we're going to talk about today. I'm going to speak about urban engineering, looking at some new solutions for urban regions, and in particular, building in objectives of resilience and sustainability. I'd like to start in Kobe, Japan, a city that I talk about frequently because it's such a perfect example of some of the challenges and issues that we're going to be facing moving forward. Kobe is a beautiful port city in south-central Japan. Along with Kyoto and Osaka, forms an important economic hub and has for several centuries in this part of the country. I go to Kobe periodically, and when I do, I stay at the Portopia Hotel, which has a beautiful breakfast room on the top floor overlooking the port. And the port facility here has been critical for the history of Japan. It was one of the very few cities in Japan that was open to the world during a couple centuries when the country was closed to everyone else. So really a key port. And in January 1995, it suffered a significant earthquake. The Kobe earthquake was magnitude 6.8, so on the high side of a moderate earthquake. But the epicenter was close to the urban region, and so there was destruction throughout. Many structures collapsed, gas mains ruptured and exploded, causing fire to rage throughout the city. Some of the more modern buildings in Japan, which is seismically very well prepared, collapsed. Portions of the transportation infrastructure were devastated. The Akaishi Kaiko Bridge, still the longest bridge in the world, was under construction at the time. And the two tall pylons you see there moved relative to one another by about a meter. The bridge had to be redesigned in order to finish the construction. And perhaps most importantly, the port facility was destroyed, all in the span of about 30 seconds. If you go to Kobe now, and I encourage you to do so, you can go to the Kobe Earthquake Memorial Museum, a really unique place, and they have docents, volunteers, and in their broken English and my broken Japanese, we had a lengthy discussion about what it was like to be in the city in the days and the months, and in fact the years following the earthquake, as they tried to figure out how to rebuild, how to recover. And the city is still trying to recover. And we see this repeated over and over again around the world. 2008, Great Sichuan earthquake in China, 70,000 people dead. 2005, Great Kashmir earthquake in Pakistan, leveled entire villages. 1976 in China, 255,000 people dead from one event. And in Japan, the most seismically prepared country in the world, in my opinion, a large earthquake, magnitude 9.0 in 2011, and the subsequent tsunami that I'm sure many of you remember took out the Fukushima nuclear power plant, and that whole region still hasn't really recovered from this event. But these aren't just events happening around the world, they're happening in this country too. Some of you might not remember the 1994 Northridge, California earthquake, but it really played a very significant role in how we think about structural engineering in this country. It was a magnitude 6.7 earthquake on the high side of a moderate earthquake, certainly not the big one. Thankfully, not too many people died, not too many structures collapsed, but it was the costliest natural disaster in the country's history. Why? Because steel frame structures, as seen in this image from the LA Times about a month after, fractured unexpectedly, at least in the eyes of many engineers and owners. The steel frame structure fractures occurred where the steel beams frame into the vertical columns. And so if you look at this photograph, for example, you'll see a steel girder flange framing into a vertical column flange, and you could see the fracture, the divot of that steel getting pulled out from the column during the earthquake. That takes a lot of energy to do, and these fractures happen in steel building structures throughout Southern California as a result of the earthquake. This is a case study that I worked on in the year or two immediately following to try to figure out what happened. This shows a couple of the steel frames in the Borax corporate headquarters, and the nomenclature there shows you where all the fractures occurred, where the girders intersected the columns. Now, the Borax corporate headquarters was less than a year old at the time of the earthquake. It was brand new. It had been designed to code by a perfectly fine engineer. This was a moderate earthquake, and the owner, needless to say, was confused. This is a private company, and it was self-insured, and so this was a huge loss. The building officials, after the Northridge earthquake, essentially shut down steel construction for a couple of years while a number of researchers around the country and practitioners tried to figure out what happened. And that will bring an economy, certain portions of an economy, to a standstill. In the structural engineering world, we use a term called disproportionate collapse. We started using it in 1968 after a gas main exploded in the basement of this apartment building in the United Kingdom that caused the partial collapse that you see here. Disproportionate means that the amount of damage that occurred seems disproportionate to the magnitude of the load, much more than we would normally want or expect given what the loading was. So we had the term, but we didn't really think about it much in this country, at least not until 9/11. Now, of course, many engineers would agree that the loads here were not disproportionately small. The loads were very large, and the fire that raged in these buildings caused the tragedy of these collapses. But that got engineers starting to think increasingly about the concept of collapse and how to start to understand that more comprehensively and build that into our designs. But the concept of disproportionate collapse isn't just for an isolated building. It also can be thought about in the context of a region, and perhaps there's no better example of that than Hurricane Katrina in 2005, which then became the costliest natural disaster in the country's history after Northridge. Because of the levee break here, of course, as you know, neighborhoods were essentially destroyed, and those neighborhoods really still, in many ways, haven't come back. Kobe, Japan, was the 6th largest port in the world at the time of the earthquake. And in a relatively short period of time, economically, it went off the face of the earth. It still hasn't recovered. The shipping traffic had to go elsewhere. They had to form new relationships elsewhere. It didn't take long for them to do that. And the city has been struggling to come back. This at a time when shipping traffic is rising and has been rising exponentially around the world. So what are the vulnerabilities in the U.S.? Well, we're certainly familiar with the high seismic zones as showed in red here on this map from the USGS. California, we understand, very high seismic zone in many parts of the state. We're learning more and more about the Pacific Northwest. We're learning more about mid-America around Memphis, Tennessee, St. Louis, Missouri, where very large earthquakes have happened in the past. Charleston, South Carolina, and even moderate earthquakes in this region are vulnerabilities. We have been improving, but we still have a ways to go. This is the port of Long Beach, California, certainly in a high seismic zone. And if we get an earthquake there, that could easily be larger than what we had in Kobe. What is that going to mean for the economy of the United States and of that region where a huge amount of shipping traffic, goods from Asia, go in and out every day? So what does it mean to be resilient, to bounce back quickly from extreme events? How do we start to bake resilience into the design of our structures in our urban regions? Superstorm Sandy was certainly a relevant event for this part of the country, and the hurricanes that can affect the East Coast are clear to us all. I'm actually impressed by how much of the region around New York City has recovered from Hurricane Sandy, Superstorm Sandy. But how many times do we need to see images like this in New York City or in Boston before we recognize that we've got some issues that need to be addressed? And of course, Boston has its own vulnerabilities. This is Logan Airport, and in fact, I applaud the engineers at Massport who are working to be leaders in the concept of resilience. Simultaneously, I think we have a moral imperative to integrate sustainability much more in civil engineering design. Why? Well, construction and use of buildings consumes about 40% of all energy in the country, about 40% of all material flow, about 40% of all waste, and about 40% of all greenhouse gas emissions through pollution. You could see that the transportation sector and the industrial sector each take up about 30%. Even there, a lot of civil engineering throughout those industries. So how can we start to develop methods that use dramatically less energy, that use less material, that contribute less pollution? This is a graphic from my colleague David Marr, and he says the method in which we're designing now in structural engineering and civil engineering is unsustainable engineering. Why? Well, the way in which we design structures now, for example, for an earthquake or a hurricane, is we ideally design the structure not to collapse, except in the most extreme loads. But the way we absorb energy from the earthquake or the hurricane is through damage in the vertical columns, the horizontal girders, the diagonal braces. The steel material will yield, stretch, have permanent damage. Concrete will crack, have permanent damage. We ideally design it not to collapse, but we don't design it not to be damaged. So you can have a relatively new building, and if you have a significant event, it might be so damaged that it takes weeks, months, maybe even years to repair. Or perhaps even it has to be condemned. This is our current state of the art. I think we could do better. And what I'd like to do today is show you a few ideas that we've been working on for the last few years to see how we can do this. The first is a project that I worked on with Greg Deerline, the late Helmut Krawwinkler, and Sarah Billington at Stanford University. Some of you have seen this idea. I've been talking about it for a few years now. But as you'll see, it's still quite relevant as we move forward. We call this a controlled rocking system, and the system for building structures has three features. First, we take standard steel brace frames like we see here, the frames that would normally be damaged in an event to absorb the energy from that event, and we allow those frames to rock free of the foundation. And then we use that motion to engage what we call replaceable energy dissipating fuses, like the old fuses in the electrical system in your basement. The fuses are shown in gold there, and they're just standard steel plates with diamond-shaped cutouts in them. We call them butterfly fuses. And the diamond-shaped cutouts allow those steel plates to shear about 40% of their original dimension without failing. They will yield the metal, but they're not going to fail. Then the third component are the green lines. That represents vertical post-tensioning that we use to snap the building back to vertical. Then you could pop out the old fuse, put in the new one, and you're ready to go again. That's one idea for resilient engineering, how to bounce back quickly after extreme events. We did a lot of different kinds of experiments on this structural system, culminating with Greg and I going over to E-Defense facility, the largest shake table in the known universe, which is outside Kobe, Japan. This shake table facility was built by the Japanese in response to the Kobe earthquake. It's one of the things they did to try to build a state-of-the-art facility. You can construct full-scale 7-story buildings on the shake table and then shake it with a 3-dimensional earthquake for very large earthquakes. We did a 3-story building here at 2/3 scale. You could see the specimen in gold here. It's a single frame in this case, where the fuse is down at the bottom center. And then the gray structures around it, those are inertial masses on each of 3 levels. And they're on linear sliders. So as we shake this shake table to represent an earthquake, those inertial masses will shake back and forth, and they're attached to the specimen, and all that inertial force is thrown into the specimen, which is the only thing that's resisting the earthquake. So 2/3 scale, this is about 30 feet tall. Each of the floors about 10 feet tall. On the right shows a zoom in on the specimen, and as that gold frame rocks back and forth in a trough, that white post will go up and down and engage the fuse, which is at the bottom center, surrounded by post-tensioning to snap this back to vertical. You can see a zoom in on the fuse on the right with those diamond-shaped cutouts. This shows a photograph of the specimen being dropped into place. We did a number of specimens and experiments over there. The Japanese were extremely helpful and put in a lot of funding on their own because they were so interested in these concepts. You can see on the right, we're ready to go here on that large shake table, and there's a person there to give you a sense for the scale. This is a video that's one of the tests. This earthquake was about twice as large as the Northridge earthquake. In the lower right, you'll see an overview with the inertial masses sliding relative to one another. On the upper part are the 2 corners down at the base. You'll see it rocking back and forth. The Japanese said like a sumo wrestler. And then the fuse, you'll see in action right here. So all that inertial force coming down into the steel fuse, which is absorbing that energy through the deformations that you see. Post-tensioning snaps this back to vertical, and we're ready to go again. Now, it's going to take some years to get this into the National Building Code because it's really a fairly different way of designing structures. Our building codes are not set up to do something with a stiff frame, and by the way, the whole point here is that those steel frames remain damage-free with a fuse. But we're working on getting this into the building codes, and in the meantime, there have been some early adopters, such as David Marr out on the West Coast, putting these systems into high seismic zones, convincing the building officials and the owners that this is the way to go. He did so in the Orinda City, California offices with a 2-story steel brace frame there for the seismic system. You can see the post-tensioning looping underneath, so you get enough length on the post-tensioning to be able to stretch and snap this back to vertical. And he used a little different configuration. Here he used deformable angles down at the base that deform when the structure rocks. You can see the post-tensioning then running up the inside of the column, and then you can use things like slotted connections or a pin connection like you see at the top in order to ensure that the rocking motion does not inappropriately disrupt the rest of the frame. Then if you need to, you can replace the angles after the major event. In Southern California, Greg Luth used this system in the University of Southern California School of Cinematic Arts. Instead of steel brace frames here, he used precast concrete wall panels that are going to rock, and he connected them with the steel butterfly fuses like you see here. David Marr used this in the David and Lucille Packard Foundation headquarters in Los Altos, California, configuration very similar to what we tested at eDefense. Oops. And since in the years intervening, I've been trying to take this idea to other types of structural systems, tower systems, bridge systems. This shows some experiments I did with Jim Lefebvre and Larry Fonstock at University of Illinois, looking at standard elastomeric bearings that sit on the underside of girders and on top of the foundations in a typical bridge structure. These are there for just minimal temperature distortions that occur in a bridge to be able to absorb those. But what we showed here is you could do large displacements like you would see at an earthquake and essentially use these bearings as a fuse because they isolate the superstructure and leave that superstructure then relatively damage-free and leave the foundation structure damage-free. So we'd like to try to take these ideas to other places. There's a new project that a few of us recently got from the National Science Foundation and from a number of steel organizations, a large grant from the steel industry. This is work with Ben Schaefer at Johns Hopkins, Matt Etherton and Sam Easterling at Virginia Tech. And the project here is to look at the three-dimensional behavior of buildings, shaking in earthquakes, as shown in the animation on the right. And in particular, look at the floor system, which is responsible for taking all the inertial force in the building and throwing it out to the seismic system, the vertical steel frames, for example, that bring the forces down to the ground. We know surprisingly little about the behavior of those floor systems, given that we're designing them every day. We have surprisingly few design provisions to guide us in the design. And so we got this project to understand that better, especially for three-dimensional buildings like you see on the left. As part of this, I'd like to look at the concept of putting in replaceable energy-dissipating fuses between the floor diaphragms and the steel vertical systems. That will essentially cushion the seismic system and perhaps transform the way in which we design buildings in high seismic zones. This will be work we're doing in the coming years out at the stress lab. This shows a schematic view of some of the test specimens that we're going to be testing at full scale to look at a floor diaphragm subjected to cyclic seismic loads. And you can see in yellow there some of the fuses that we'll try to incorporate here. Now, when we're developing new structural systems like this, we also want to think about how to prevent collapse. And of course, in our field, we do a lot of experimental simulation and computational simulation, but historically, engineers have not actually been simulating structures collapsing all the way to the ground because it's difficult. So in the last few years, I've been developing some methods with my students to do just that, and in particular, some new approaches for simulating fracture in steel so you can actually have complete dismemberment of steel components and therefore propagate collapse to the ground. This is a test from the National Institute of Standards and Technology where they had two girders framing into a column, and then they're mimicking what would happen if that column below was blown out, for example, in an explosion, and then the weight from the building above pressing down on that column. They wanted to see how the structure would behave and if the connections would hold up. So we compared to the test. You could see in the plot there of the vertical load versus vertical displacement. Very nice comparison, and here's an animation that shows the stress buildup in the connection regions and, in fact, the fractures starting to form here. We've developed new approaches to be able to create and simulate the initiation and propagation of those cracks. It's quite difficult to do. And we have validated now against a wide range of other experiments. And you can see here we're matching up with the photographs of the experimental tests quite well. So we think this is quite robust and is going to start to let us model collapse of structures completely to the ground. And therefore, of course, try to develop methods to prevent that from happening, and indeed help make that urban region more resilient. Simultaneously, we're thinking about sustainability, how to cut down on energy use in construction, for example. And one system we've been working on for a number of years relates to steel structures. The end-of-life scenarios of typical construction materials are shown here. On the left, we can see what happens to concrete after buildings, for example, are taken apart. About 20% of the concrete is recycled, 75% of it is downcycled, meaning it's essentially pulverized and then used in applications that don't require as much stress, such as sidewalks. Timber, which many of us think as a very sustainable material, about 60% of it goes to the landfill after its use. I hope the younger generation can develop systems that improves on that. Steel, on the right, we see about 93% of all construction steel is recycled, and indeed about 100% of all the steel you see in building structures comes from recycled steel. So that's good. But recycling also requires energy to melt the steel back down. About 6% of all steel is reused, and I'd like to see that percentage go up dramatically. So for the last several years, we've been working on a project we call Design for Deconstruction. This is done in collaboration with Mark Webster at Simpson, Gumpertz, and Hajjar, a practitioner. Steel building structures right now are constructed by having steel framing for your floor system and then a monolithic concrete slab poured on top and connected to those steel girders with what we call shear connectors that are embedded in the concrete and welded to the steel. It's not deconstructible at all. So at the end of a building's useful life, the building has to be demolished. The floor system has to be demolished. We envisioned something different, and here we're using precast concrete planks in a staggered pattern like you see in the floor plan on the right. And those planks are going to be attached to the steel beams underneath with clamps. These clamps are relatively new on the market. They're very strong, and so we use the clamps to attach to embedded channels on the underside of those planks. This is a system that Mark conceived of early on about a decade ago, and pleased to get some NSF funding to be able to look at this. And we view this to be used in the context of all bolted steel construction. And so at the end of a useful life of a building, you can dismantle it, you can deconstruct it, and reuse the planks. You could stock them in a supply center, just as we do now with new steel beams. And then you can deconstruct the steel beams and columns and reuse them. Most buildings are taken down at the end because the owner doesn't want them anymore, not because they've been subjected to some extreme event. And of course, if the structure is subjected to extreme loads, well, then you probably can't reuse the components, but the vast majority are not. And we'd like to create a whole new industry around this. So we did some tests out at the stress lab to validate the structural integrity of these systems. And on the left are what we call push-out tests. These are just tests to look at the strength of the clamps under cyclic seismic loading. But I want to show you some results from the system on the right. This is a full-scale composite beam, we call it. It's got a steel girder with 15 of these precast planks on top connected with the clamps. And then we use those vertical actuators, the two of them shown in black there, to push down with extreme loads. These are simulating the loads that you'd have on a floor, just like we do in this room here. And we want to make sure that the structure has integrity. So this video shows the vertical load versus vertical displacement on a couple of our tests. The middle video on the right, these are time-lapse, the tests take hours, shows you an overview of the specimen so you can start to see it deflecting down as we press down with these actuators. And then the other two views show the steel beam and the underside of the concrete slabs. You could see on the bottom right the clamps as we shoot down the length of the beam here. And what these results show is that we could transfer the force necessary between the concrete and the steel very effectively, and in fact, What's quite new is essentially damage-free. And so a damage-free approach to force transfer is what enables these components to be reused. Now, simultaneously with developing new types of structural systems to try to be resilient and sustainable, we've also been working on new methods for monitoring structures and being able to quickly and effectively understand what the damage is on a structure, both for routine inspection and especially after a significant event like an earthquake or a hurricane. I've been working with colleagues at the Robotics Institute at Carnegie Mellon University for the last several years on this, using unmanned aerial vehicles to completely and autonomously circumvent a structure. The UAVs, as we call them, are mounted with laser scanners and cameras that take a complete 3D point cloud and a lot of camera images of the structure, which I then use to reconstruct the three-dimensional geometry, develop analysis meshes, which we use to simulate the response of the structure, and most importantly, we use those laser scans and images to automatically detect damage. So this shows a series of videos that give you an idea of what we're doing. On the left, the unmanned aerial vehicle is autonomously flying around the structure. So these are not drones. They're not piloted. They're completely autonomous. And through the laser scanner and the images, it builds up the point cloud, the colored point cloud that you see here. The colors are coming from the camera images mapped onto this 3D point cloud. Then on the upper right, we use that point cloud to automatically identify every object in the structure. And we've developed the algorithms to do this. They're heuristic-based, meaning that we are essentially mimicking a structural engineer's understanding of how a structure is put together. We have developed algorithms for occlusion, so understanding that members are hidden behind members, bolts going through members, and then from there we create the complete three-dimensional geometry, understanding every object, and then we mesh it. You could see the small squares there. This breaks that geometry up into small cubes, which we can then use for what we call finite element analysis to simulate the stress, the strain, the displacements, as we see on the lower left when we start to subject this structure to extreme loads. You can see the deflections going on now, typical loadings on a bridge like this, so we start to understand where the damage may be coming from. Then on the lower right, we go back to the point cloud and use that to automatically detect damage. Steel section loss from corrosion, bent members, out-of-plumb members, concrete cracking, concrete spalling, and other such types of damage. Over the last several months here at Northeastern, Tashkin Padir, Peter Boynton, Steve Flynn, and I obtained a grant from the Department of Homeland Security and the Global Resilience Institute right here at Northeastern to take these technologies and start looking at post-event automated damage detection, now looking at structures after a major earthquake, after a major hurricane. So we're going to be doing that moving forward. This is a little bit more difficult types of damage to detect, but our fabulous students will succeed. Simultaneously with this work on the built environment, very pleased to be able to be participating in some major research to bring renewable energy to our country, and in particular to this region. We've been working on offshore wind for some years now with grants from the National Science Foundation, Massachusetts Clean Energy Center, and other places. This is work going on with Andy Myers here at Northeastern, Sanjay Arwadi at UMass Amherst, and Eric Hines, who's at LeMessurier Associates, practitioner, also at Tufts University, and a real thought leader on this topic. As many of you might know, the country's first offshore wind farm just got installed a couple years ago off the coast of Block Island, down in Rhode Island. It's called Deepwater Wind, and it has 5 offshore wind turbines that you see here. This can provide 30 megawatts of energy. Department of Energy has set a goal of having 86 gigawatts coming from offshore wind by 2050. 86 gigawatts is about 7% of the electricity need in the U.S. Personally, I would like to set much higher goals than 7%, but this is what we've got so far. Now, off the East Coast, 86 gigawatts would represent 4% of the wind capacity for offshore wind. If you do the math, what that means is there's enough wind capacity off the East Coast to power the entire country, and then some. Think about that for a second. And nowhere, and certainly we could power the East Coast. And nowhere is that better than in Massachusetts. This is a graphic from the National Renewable Energy Lab that shows the offshore wind capacity of every coastal state in the country, and way over on the left is Massachusetts, showing supreme capacity both for shallow water and for deep water. Now, I'm sure a number of you have heard of Cape Wind, which got a lot of press for years. This was an offshore wind farm that they tried to develop, and it actually got pretty close, but it's not going to happen. But in the ashes of that project is going to build an entire industry. And the federal government and Massachusetts have leased these much larger areas, much further offshore. You could see the leases there went for several $100,000. Well, in the months or a year or two after, up and down the East Coast, there were more leases going for tens of millions of dollars. This is an industry that is about to explode. And there are companies coming in from Europe, especially from Asia, who've been doing this, for example, out in the North Sea for 2 decades, saying, we want to be the ones who are building this here. Here in Massachusetts, we're saying, we want to be the ones who are building this here. And we would like to help create this industry by building the research infrastructure and the workforce development to do it. Now, Massachusetts understands this. The state legislature understands it. The governors understand it. There's been some great leadership here, especially from the Massachusetts Clean Energy Center. And so there is some hope. The issues on the East Coast are potentially quite different than what's been happening out in the North Sea, for example. Why? Well, for one thing, we have hurricanes. And you could see here what happened to the onshore wind farms in Hurricane Maria in Puerto Rico just last September. Our soil conditions are different. Our supply chain is different. Our hurricanes are different. Our loadings on the structures are different. We're going to need some research to understand how to do this properly. And so, very pleased that we've gotten a good head start on this. Through the grants I mentioned before, we've been looking at the impact of hurricanes in this region, and in particular looking at the combination of wind loading and wave loading on offshore wind turbines to understand how to design them better. And have been looking at monopile towers and jacketed structures like the truss structure on the right, and developing approaches for design that we think are going to be more robust, certainly in this region. We call this performance-based engineering, where we look at the desired performance at different levels of loading, for example, different levels of hurricane, and then develop methods to predict that and ideally to prevent unwanted damage from happening. And in addition, the schools in this region for a number of years now have not been working in competition with each other. They've been working collaboratively. And the Massachusetts Clean Energy Center gave us a grant a couple of years ago, to form what we call the Massachusetts Research Partnership. And it includes Northeastern, Tufts University, UMass Amherst, UMass Lowell, UMass Dartmouth, and Woods Hole. And then a few other Massachusetts institutions have been starting to participate as well. And our mission with this grant is to write a report that's going to be coming out this summer that documents, ideally for an audience consisting of the federal government and the Department of Energy, what the needs are to build a national research infrastructure to create research in offshore wind so that we can create the industry and help create the industry for offshore wind. Now, as part of that, we've also started communicating with and collaborating with virtually every major player doing offshore wind in the country, and you can see that here. And we formed an organization called Power US, Partnership for Offshore Wind Energy Research. And great to see these institutions, including some of the national labs, working collaboratively on this to try to make this happen. And in fact, next Monday, the Massachusetts Clean Energy Center is putting in a $20 million grant to the Department of Energy on behalf of most or all of these institutions to form the first major research consortium dedicated to research on offshore wind. So that's happening right here with Northeastern participating. Very glad to be a part of that. And we'll see what happens in the coming years. Now let's finish off by taking this up to thinking about whole urban regions and how we think about resilience and sustainability in urban regions. And the work we're going to be doing in the next couple years, and I've been working on this for the last couple years on an NSF project, is with the 8 faculty that we have up there. These are from all at Northeastern. Mario Sneyer is the principal investigator. They're from colleges throughout the university, so truly an interdisciplinary team, and it's been great working with them. And this is one of the NSF CRISP grants, Critical Infrastructure Resilience. Our goal is to try to make the emergency healthcare system in an urban region more resilient, and in particular, we're looking at urban coastal regions that are subjected to hurricanes and storm surge. And we're going to be looking at the power network, at the communications network, at the building stock related to critical facilities like hospitals, police stations, fire stations, and so on. We're going to be looking at people before and after a major event and modeling, doing some agent-based modeling of the people and of the decision makers. And then putting all that together to do simulations where we develop control methods to try to control these networks and control these systems to make them more resilient, to be able to bounce back more quickly after extreme events. So my part of it's on the civil engineering side. This shows the recorded hurricane storms from the National Hurricane Center in the United States. A little bit of a disarming figure. And what we're going to be doing is simulating hurricanes. For example, this is the track of Superstorm Sandy. So we'll be developing simulation methods to simulate those hurricanes and their impact on urban coastal regions. We're going to be using Boston as a test bed. So in order to estimate the damage that occurs from these hurricanes, we first need to have all the assets in a region. So we're currently collecting information on every building, ideally, in the Boston region, every roadway, every bridge, every power infrastructure, communications tower, pipeline infrastructure, whatever we can get. So through this, we have to establish properties on these that we're going to use to drive our simulations. For example, building age, going all the way back to 1700, shows what kind of building code might have been used to design it, and then we can try to account for that in our simulations, et cetera. And so from there, we're going to simulate the impact of the hazard. Now, we haven't quite done this yet, but I give you a forewarning from the U.S. Army Corps of Engineers on the Boston region. 4 different levels of hurricane. This shows the likely storm surge inundation. Can you locate Northeastern there? Yeah. What I'd really like to bring to this, though, is the concept of resilience and developing new methods that account for new types of systems that can bounce back more quickly, incorporate those in the simulations, and be able to show the advantages of using these. This shows a typical functionality curve for building functionality on the vertical axis versus time. And you can see a building is functional and then an event hits and it drops down. And the question is, how quickly and with what types of systems can we bring these back quickly? And then we'll feed that information. I'll feed that information up to our network modelers in electrical and computer engineering and other parts of the project who are going to start to understand the behavior of damaged networks, of damaged healthcare systems, and how to make these systems more resilient as we move forward. The concept of resiliency is relatively new in the United States. Many of you are familiar with the concept of LEED, where buildings can be rated gold, silver, gold, platinum, et cetera, for LEED. That's trying to account for sustainability. How much sustainability? How much did it decrease energy use or material use, et cetera, in buildings? And I'm not quite sure if LEED is really doing what we're hoping, but it's a start, and it's certainly getting a lot of the public talking about it. It's getting the owners talking about it. Everybody tends to have a general understanding of what LEED means. The U.S. Resiliency Council, which is relatively new, would like to do the same thing on the concept of resiliency, bouncing back quickly after extreme events. So they've established silver, gold, and platinum rating system. So now when you're choosing what buildings you want to live in or choosing what buildings you want to work in, maybe there'll be a resiliency rating so you can actually understand whether this is going to bounce back quickly. Now, and I would venture to say, sustainability, we all understand the potential importance for that, but resiliency is the real thing. If where you live gets hit by a major hurricane or a major earthquake, this is something you might want to understand. These are the kinds of simple things that can actually change a culture. And I'm hoping this happens moving forward so that, unlike the Goldman Sachs headquarters in Superstorm Sandy, which was an island of resilience planning amid a sea of darkness, we could start to do better across entire urban regions. A few years ago, one of my postdocs and I worked on a concept called topology optimization, which is an idea in structural engineering that's a little bit more freewheeling than typical standard optimization methods for designing structures. The idea is that you take a building and you start with just a mass that represents, the mass of the building. Then you subject it to loads, for example, a hurricane. And then the topology optimization algorithms will optimize where the material needs to go to resist those loads, but they do not constrain themselves with our typical constraints that columns need to be vertical and beams need to be horizontal and braces need to be diagonal. Instead, you can develop more freewheeling forms like you see here. These are potentially more organic forms. Of course, you have to think then, what about constructability? Well, one of the greatest structural engineers in the world, Bill Baker, has been using these ideas for structures at skid moorings and Merrill, and you could see some of the natural organic forms for the mega bracing that he has here. These systems just feel right, and they feel efficient, and indeed, they can be, often are efficient. In fact, ideas like this have been around for a long time, and I'd like to bring the concept of topology optimization in the years to come to start thinking about regions, urban engineering of regions. Of course, there are many constraints in an urban region, but as we start to integrate objectives of resilience and sustainability, can we have a little bit more free flow of our ideas, free flow of understanding the geometry of a city, to be able to really start to get some new solutions in here that might upgrade our capabilities significantly. Something I hope to do in the years to come. I just want to finish by thanking again all of the collaborators on these projects. There have been many, all of the sponsors, especially all of the students who have worked so hard on this work. The collaboration in general here from all of my colleagues at Northeastern has truly been wonderful. It's been a great ride. I am very appreciative. Thank you very much.
Thank you. That was really terrific. And we are really grateful to have somebody like you working on that stuff, given that Boston graphic. So
there you go.
Thanks for being in there for us. We'll have a few minutes for questions and answers, then I get to give you a medallion, then we eat and we drink. So I'll leave it to you to take the questions from the audience, if you don't mind.
Okay.
And there's a microphone going around so that the people who are listening streaming can also hear.
Sheila Pufford, DeMoore McKim School of Business. Thank you very much for a fascinating presentation. What about the factors that are impeding progress, such as the human factor and industry standards, and trying to change those, and some of the stakeholders, such as current manufacturers of some of these products who may not want to have competition from sustainable products?
Mm-hmm. Yeah, that's a great question. So the question was, what do we do about some of the embedded culture that we have now, humans who don't necessarily want some of these changes, industries that don't necessarily want some of these changes, current national standards that don't have these changes embedded. And I would say, as I mentioned earlier, for starters on people, it's going to take a culture shift. This is a culture shift. And for sustainability, we're going to need to start looking at certain things out there. And you know, I work a lot with architects, and when you're working with architects and you're designing structures and you're working with the owners, the architects could say to them, well, why don't you do this? It's going to be beautiful. And the owners would say, oh yeah, that's a good idea. But when you talk about sustainability and saving energy, whoop, the calculator comes out and they start calculating the cost. It's going to take a culture shift where things that are unsustainable look ugly. And then we'll start to see this shift, where structures that are not resilient just don't feel right to us. And then we'll start to see the public policy follow. I think the professions can address the industry standards. If these are safe and effective, over time, I think we will be able to integrate them. Now, in terms of the major industries, I prefer to try to float all boats. Perhaps that's naive. There are some industries that might not be approving of this. I'm not sure I have an answer to that one. Yeah. Tim?
I have it, Tim, so I'll go first.
Oh,
Okay. So, Jerry, there must be industries outside of the construction industry that will be allies. The first one I can think of is insurance. How is this not becoming a major driver from the insurance industry?
yeah, that's a great question. So, insurance, how is this not a major driver for the insurance industry? First, I would say there are some forward-thinking insurance companies, and in particular reinsurance companies, and in particular the consultants who advise the reinsurance companies, who understand the ideas here are potentially beneficial. So there is hope for the future in that sense. However, I've also learned that the insurance companies are pretty smart, and basically they set a premium, they set a cap on damages, and they almost don't necessarily care what happens in the middle. But there are companies, some of them in fact are located right here in this region, that are real pioneers on this, and I think they could be helpful. But their thoughts are not uniform on this topic.
So, Jerry, that's an excellent talk. I learned a lot as a non-engineer. Thank you very much.
Yep.
I, of course, go to public policy, and you started to touch on this, but do you think that there are policies that we could be putting in place, more legislatively rather than regulatory, that could incentivize this new approach?
Yes, absolutely. So the question was, are there policies or regulatory things that we could do to incentivize these types of approaches? And the answer is absolutely yes. So let's start with offshore wind. Some of you might know Massachusetts passed, I think, the first state law mandating that a portion of electricity use come from offshore wind by a certain year. So that's a simple example of something that can drive things forward. Perhaps more importantly, the federal government, for its own buildings, sometimes is a leader on these topics, sometimes. So for example, General Services Administration, which oversees a lot of federal buildings, if they start saying, we need resiliency in our building designs, or I think they have been saying we need sustainability for many of our building designs, that will help drive the industry standards. There's a parallel to this going on right now on the concept of performance-based engineering. We've been trying to get performance-based engineering into our building codes for 2 decades with very little success. Then somebody in the federal government, I'm not sure who, decided that all GSA buildings need to be designed by performance-based engineering, and the building codes are scrambling now to write those provisions. So yeah, there can be some public policy that can drive this very quickly if it's in the right place at the right time.
Good afternoon. My name's Mike McGrath. I'm a civil engineer and registered professional land surveyor. I practice in Falmouth, Massachusetts, and we're on the verge of some major changes in our environment. I just wrote an opinion for Woods Hole, and I have told them that the special flood hazard areas elevations are not correct. They need to be elevated by 2 feet. We're talking about an area where the tidal range is only 20 inches. And so the other thing is that we have seen that the water temperature of Buzzards Bay was the highest in history in 2016. And I live on the shores of West Falmouth Harbor, and I have to tell you that mean high water is a foot higher and mean low water is a foot higher. Those are approximations. I don't know the precise. So we're beginning to see some major environmental changes that are occurring. And so what Jerry's doing is going to be needed in the future.
Thank you. I agree with you. Hey, David?
Jared, regarding the topic of culture, do you find that maybe the Japanese government is farther along the culture path than we are, or are there some governments that are farther along, and what are they doing differently?
So are there other governments that are farther along on these topics? That's a complicated question. I think it's fair to say, perhaps, that Europe is farther along on integrating concepts of sustainability into the built environment. With respect to resilience, really being able to bounce back quickly, I don't see any governments out there that have really embraced this. We still need to design a lot of the solutions. We have not been designing this into our design procedures. No, I haven't been seeing that. I think we have a ways to go. Okay, well, before we break to Deb, if it's okay, I'd like one brief moment of indulgence. My spouse is here, Lauren Tafe, and I just would like to thank her for all that she has done. Would you mind? Thanks a lot, everybody.
That was a great addition, thanking your spouse. So on behalf of Provost Jim Bean, photographer who wants to get that just right, I present to you the medallion for the 2018 Klein Lecture. And I think I can reach you with the Velcro, and there we go. Thank you very much.
Thank you very much.
And now we have some nice food out in the hallway. We have some drinks here which need to be drunk in this room according to our police department. So please enjoy yourselves for now. Thank you all for
Hey, thanks a lot, everybody. Thanks for coming out. Thanks.